Good morning, everybody. Do you want to see my new tattoos? Woo! Yeah, Band-Aids and to cover up the tattoos. No, they drew all over the back of my neck and then they stuck 6 needles in. So they had fun. I have no memory or awareness of anything that happened. They said it went well, so I guess I just have to trust them. I did ask the anesthesiologist. I said, "You are giving me the stuff that makes it so I don't remember, right?" She's like, "Oh, yeah." So I got immediate relief because they inject first lidocaine, which is a drug that just deadens nerves from feeling anything. And it's great stuff. And then, I woke up and I was like, oh my gosh, I can feel my fingers and they don't hurt and all this kind of stuff. And then sort of slowly over the course of the day, the lidocaine wore off. They also injected steroids, not the anabolic kind. So I'm not going to get ripped, right? It's too late for that. But they injected steroids to try to calm down the inflammation that's around the nerves that are coming out of the openings in my spine. And so it takes about 2 weeks for that to sort of ramp up and get to its highest strength. But I already am feeling a little bit of relief, which is good. Thank you to everybody who emailed and asked. Appreciate it. Unfortunately for you, I am still alive. And we will still be doing the exam on week from today, right? I decided today was not a slacks and button-down shirt day. So I won't ask for your permission or your apology. It's just the way I am. Also, I couldn't get my shirt to work well with my Band-Aids. The other thing about that, those of you that have requests for exams to be taken over in DSPS, make sure you get those to me so I can get those put in. And I think that's it. What are we doing in lab next week?
Studying.
It's your review time, right? Okay. Come in, ask questions about the exam. Please tell me I posted the topics.
Yeah.
Okay, that wasn't a fever dream from the steroids. Okay. I've had about 4 hours of sleep in the last 24 hours, so I'm feeling a little bit punchy and can't remember exactly what's going on. So please forgive me. Let's see, though, if I can do physics on automatic pilot. Yeah, oh, right. Okay, so air friction. How do parachutes work?
The word you just said.
Air friction, right? Okay, because, okay, I did this, was it last year? My father-in-law, who turned 80, wanted his 80th birthday present to be falling out of an airplane, so we obliged him. I went with him. I much preferred after the parachute was open. The free fall was really cool. A lot of people think that there's going to be some sudden, your stomach drops out or something because you're falling. The plane's already going 100 miles an hour, and then you are going to be going 120 miles an hour in free fall, and not in free fall, at terminal velocity. And going from 0 to 20 miles an hour in the space of 300 or 400 feet just simply isn't that much acceleration. What they don't warn you about is the brick wall that you hit when you jump out of the airplane, which is called the air, right? It's roaring in your ears. It's taking all the flabby skin of your face and pushing it back. Got some hilarious pictures that I forgot to bring, but it's quite the experience. But after the parachute opens, it's like serene and kind of quiet. And it's just this nice glide to the ground. So I preferred the second part to the first part. Next time, open higher. We'll be good. I'll hold my breath from 14 down to 12. We'll be good. All right. So anyway, parachutes work by causing larger air resistance, right? A parachutist isn't in free fall because you got all that air friction acting against them. But when the parachute opens, the air friction suddenly gets bigger, right? We've got a much bigger surface area from that parachute to catch that air, increasing the air friction, and then slowing the parachutist down. So there's a lot going on there, and it would be really hard to do that from the point of view of, say, Newton's second law. In fact, when you jump out of the airplane, the acceleration is close to free fall acceleration, but then very quickly gets to basically zero when you hit terminal velocity. And so you've got a changing acceleration the whole way you've jumped out of the plane to terminal velocity. What's the acceleration once you're at terminal velocity? Once your speed's no longer changing, it's going to be 0. But then when you open the parachute, all of a sudden, right, acceleration goes down to 0 to then suddenly up, right? As you slow down, you're moving down but slowing down, right? So you've got all these different accelerations going on. We'd have to whip out some integrals. We'd have to invent a new kinematics toolbox. It's a pain. If we need to understand completely the dynamics of what's going on, sure, we've got to do that. However, if we're just trying to ask questions like, what is the speed that the skydiver lands when approaching the ground, right? Then we don't care about time or acceleration or any of these things, and we can use conservation of energy. So we need to start with a visualization and a strategy. So either way, sometimes I just get the work energy equation just down. I just get it down, right? To ground myself and remind myself, like I'm looking at this thing. What is this I and F trying to remind me of or tell me to do in my visualization?
Initial and final.
Make sure you get an initial and final, right? The only thing this thing doesn't explicitly say is I need to pick 0 for gravitational potential energy. But so that's just one thing I got to remember. Okay, so let's see here. Skydiver jumps out of airplane. And let's see, where's my skydiver? Right there. All right, jumps out of airplane, falls a distance. Now they tell me, they kind of tell me this distance, right? Altitude. Altitude is always a number as measured from above the ground. So if the entire plane was 1,000 meters, right, above the ground, and we're opening the parachute at 200 meters above the ground, then what's the other number? What's the, without the parachute distance? It's 800, right? Yay, we can do subtraction. Okay. So there we go. And, I've got a picture now. Where's my initial? Where's my final? Where's my 0? Let's do 0 first. Where's 0 going to be? Yeah, let's just put it at the ground. Mr. Balogh likes to put it as low as he can in the problem. Okay, and then initial? At the top, right? Where it jumps out of the plane? Yeah, that's where it started. And where are we going to end?
At the bottom.
Landing on the ground, right? We're going to trust that energy, conservation of energy, can handle everything else that's going on. I do realize that there's sort of some people have a gut reaction like, okay, well, I'll just do this part, right? And because that's a different force, isn't it, than this part? So since this force is different, I'll do this part. And whatever final speed I get, I'll put it in as initial speed for this part and then do it all over again. Like, we've had to do that with kinematics. I totally understand, right, somebody doing that. But energy can do the whole thing. It really can. It's like magic. But we call it science. Okay, so let's tackle the work others first, because we do have these frictions that are acting in the problem. In this top part, it's 50 newtons, isn't it? Okay, and then down here, right, this force is 50 newtons. The force, we'll call it 2, F1, F2. This one, what do they say, 3,600 newtons? All right, so how do we talk about work other? Remember, work other is any force that's not a spring or gravity. And I've got 2 of those. I got a 50 Newton force and a 3,600 Newton force. So this term, this work other right here, is going to act like a sum. It has to be the total. Just like energy initial is the total of kinetic and spring potential and gravity potential. And the final, same thing, right? It's kinetic, gravity potential, spring potential. The work other represents the total amount of work done by other forces, plural sometimes, in the problem. And we've got 2, don't we? And I'll just kind of be a little bit careful here as I work this out. It's the work done by force 1 plus the work done by force 2, right? That's my work other term. And then I've got kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. I don't always write this line out, but I am trying to help you. I'm trying to be clear, right, as to my thought process so you can see kind of what I'm thinking about in these different terms. So this part right here was the work other. This part right here was my energy initial. And this part, apparently I'm feeling colorful today, was that part right there. I hope that makes it clearer and not more messy. Okay. Should we just go at this from left to right? See where we get? Okay, what's work due to F1? What is work in general? Force times distance, right? And a cosine theta in there. But all of these things are up and down, aren't they? It's not like we have anything at some weird angle. So we don't have to worry about angles. But we do need to worry about like direction or the idea that forces and directions being opposite each other become negative. Now, what kind of friction is air friction? Static or kinetic? It's kinetic. That you are moving, the parachutist is moving with respect to the air, right? So air resistance is a kinetic thing, and so what will the work be, positive or negative? It's going to be negative. The force is up, isn't it? But the direction the parachutist is going is down. So that gives us negative work. And now that we've got our positive negative work, and we know that it's force 1, and we know it goes for a distance 1, I can symbolically write down what that work from force 1 is. And then I add on, it's a sum, another negative work. This time the work that's being done in the second part. It's a different force, it's a different distance, so it's going to be a different amount of work. Which one of those 2 works is going to be bigger? The bottom one, right? It's a lot. It's smaller distance, but way more force. Okay. We hope. It's the idea of a parachute, right? Okay. Kinetic energy initial. 0. We're not given any information about, I mean, I know parachutists in a plane would be moving, but this one, you notice I said balloon. And technically balloons don't really go that fast. So we'll say it's 0. So that means that there is no kinetic energy initial. What about potential energy? What 2 things are you trying to think about with potential energy? Spring and gravity. Are there any springs in this problem? Can we agree to never mention springs for the next 5 minutes? Good. All right. So just gravity. Is there gravitational potential energy up here? How do you know? Not at 0. Right? The only place where there is no gravitational potential energy is at 0. Anywhere else is going to have gravitational potential energy. So that's definitely there. Formula for potential energy? mgh. All right. Equals. All right. When we get to the ground, is the skydiver moving? I know you want to say no. Thank you for those of you that said no, but that is the wrong answer. How do we know that they are moving? Right? Eventually it will be 0, right? But that would be a third work term, wouldn't it? That would be the ground force acting on the skydiver as they slide across the ground or do whatever, right? Okay? So what we're talking about is like in that instant right before it hits the ground. And we could tell that because it's asking for the speed. If we didn't put in a kinetic energy term here, we'd have nothing to solve for. Okay? So let's see here. That would be 1/2 mv squared. And then is there any gravitational potential energy at the ground? No. I hope the takeaway from this, you're not concentrating so hard on the math that you forget to see the entire forest. Don't look at the trees. This is a methodical process. I've been modeling for you the questions that you should be asking yourself as you go through, right? Does this exist? Is there kinetic energy? Is there anything besides gravity or springs that I need to account for, right? Sometimes if you try to just drive directly to the equations, you skip all that hard thinking stuff. But the hard thinking stuff really does make the rest of the problem solving process flow. So, I mean, this line, these two lines right here are fairly generic, right? We've seen similar things in all the problems I've done like this so far, right? So in some sense, all of these problems kind of start the same way. Sure, pictures are different, right? But the layout and the attack of what we're trying to do here stays. This part right here is very specific to this problem. So, all right. So let's, sometimes we just need to clean up a little bit. But what are we solving for? We are solving for this V right here, aren't we? Can I just cancel my math? No. Why can't I do that? It's not in every term. So I can divide it out of the MGH as long as I do what? Divide it into every term, right? If I divide the right-hand side by m so that I can cancel it out, right, then I have to divide all of the terms on both sides by m. Otherwise, my equal sign, no worky. Okay, and then how do I get rid of the 2? I multiply by 2 on that side, but that means I have to multiply by 2 everywhere else, right? That was awkward. Okay, so this is why I usually skip math steps, because it gets messy. What have I got here? I have got, I'm going to turn it around first. V squared equals, I'm just swapping the way I write this thing. And then I've got 2gh. We've been here before. Square root of 2gh, we've seen that before. But then there's some extra pieces here. Let's see, I'm going to write minus 2 over m. And then it's going to be f1 d1 plus f2 d2. There I did do several math steps. I factored out the minus sign. These minus signs right there got factored out, along with the 2's and the m's. That's what that minus 2m is sitting right there in front, okay? And then because I factored out a minus sign, I ended up with positive FDs. And I think everything over here now is a number that I know. 2 times 9.8. What height do I put in here? This is where the other part we got to be really careful. What number am I going to put in for the height? It's 1,000, right? This was a potential energy initial. It was like a height initial. Our 0 is down here at the ground. It's 1,000 feet above the ground. I'm not going to put in 200. I'm not going to put in 800. Okay? The height that this thing started was 1,000 feet above the ground. So I'm going to put 1,000 in there. Minus 2. Did they give me mass? 80. And then what do I put in for F1? That's 50. And D1 times 800 plus 3,600. And how long did the 3,600 act? It asked for 200. All right. I don't know if anybody's doing this in their calculator, okay? But I do have the answer here with me. Does anybody want to take any guesses? Somebody that hasn't done it in their calculator. A guess is for how fast they're going when they hit the ground. 27 meters per second is about 60 miles an hour. 30? Are you going for like smushed skydiver? Yeah? 10. So 10 meters per second is like would be like Usain Bolt running the 100 meters in the Olympics, right? Right? So that's like 35 miles an hour, 32 miles an hour, or something like that, right? That's not a good day. You really want to have less than 5 meters per second. Ideally, you want to hit with less than 5 miles an hour, which is like 2.5 meters per second or something like that. But this number turns out to be 24.5 meters per second, which is more than likely a deadly landing, okay, assuming it's straight down into the ground. So that's no bueno. And to make it bueno, we have part B. And you should have known it was not going to be very good, right? By the nature of the question, right? So what does part B do? Like, what's the switch? What are we solving for now? Is there something up here that I wrote down that I'm solving for? It's D2, isn't it? They're asking for at what height, right, would we open the parachute so that the speed would be, was it 5 meters per second? Which still isn't nice, but better than 24.5, okay? So can I come up here and like recycle this line? So that line right there was spent, right, it was written down and then we started solving for V, right? But we could instead solve this line for D2. What would this line look like? It was in red, so F1 D1 with a minus sign, minus F2 D2 plus mgh equals 1/2 mv squared. That's where I started initially, right? This is part A, and this is part B now. And I can just take this line and recycle. Has the physics changed at all? Like, have we started at a different height? No. Are there still two works that are being done? Yes. Are there still no springs? The work energy statement that we put down for this problem can be recycled in this problem, right? Because we haven't fundamentally altered, we haven't changed the parachute. All we're doing is changing a distance, right? Solving for a distance with a known velocity this time. So rearranging this, oh, wait a second. We've got additional issues. I don't know what D1 is.
Just D1000 minus D2.
We've got two unknowns. And you're right, okay? But this and this are both unknown. If I don't know what D2 is, I don't know what D1 is, right? But we can find out. Because what's the relationship between D1 and D2? When they add up, they need to be 1,000, right? So if D2 is, I don't know, 400 meters, what will D1 be? 600, right? So what I do here is I solve for D1, it's 1,000 minus D2, and then I can go ahead and stick that up into this equation. And when I do that, I get negative F1 and then 1,000 minus D2 minus F2 D2 plus mgh equals 1/2 mv squared. I'm not gonna do all the algebra that's required. You got to multiply through that F1 and then gather the D2s by factoring out the D2s and then move everything else over to the other side. That's algebra. It's boring. Does anybody want to take any guesses as to what the actual opening altitude would need to be in order for this to be 5 meters per second? 800? Open it early? 1,000. Certainly would guarantee a safe landing, wouldn't it? This turns out to be 206 meters. Just a 6-meter difference, spelling the difference between life and death, right? In this very contrived, but actually based on real life practice in the military. My anesthesiologist yesterday, she had served 2 tours of duty in Afghanistan. And she actually had the naval insignia on her scrubs. And I looked at it and I said, "You were in the Navy?" She's like, "Oh, you noticed?" Yeah, so I got to talk to her for a while. The people that serve in our military are amazing in many different ways. But I've had people that I've known that have done a kind of parachuting called halo jumping. This is a picture of a special services operator jumping out of an airplane. I picked this particular picture because, do you see it? There's a dog. Yeah, okay, there's a dog attached to that surface person. Yes, some of our service, the reason I know is because my mother does training for seeing eye dogs for the blind, and there's some crossover with the military dogs. But they have a dog attached to them, and the dog is muzzled and blindfolded. In all likelihood, it looks like they've got a blindfold on, because dogs are smart. They won't jump out of an airplane just because, right? They're like, duh, I wouldn't do that. So they get strapped on to. Initially, dogs were trained to jump out of airplanes. Well, they weren't trained to jump out of the airplane. They were trained to parachute. And in the training footage, you can see the handler. So the dog has like an oxygen mask, because they were doing it way up high, and the muzzle and the blindfold so they couldn't see. And then they had a harness that had the parachute on it with a big handle, right? And the handler just walked to the end of the airplane, picked the dog up, and chucked it out, right? The dog had been trained, right? So it wasn't startled or anything. The dog just went, right? And then the dog's parachute would open automatically. And when it hit the ground, the blindfold mask would come off. And then the dog was trained to go find the handler, wherever the handler landed, because the handler chucked the dog and then jumped after it. So now I think they do more of an attached type of thing. The parachutes have gotten better. Anyway, this is halo jumping, high altitude, low opening. They joke that if you do it wrong, you might be wearing a halo. Do it right, okay, and you can do it. Why would you want to jump out of an airplane way up high only to open the parachute at the very last second? So let's say you want to get in underneath a mountain where there's an observatory or a radar station or something like that, right? A body falling through the air has virtually no radar cross-section, meaning it's very hard to detect on radar because they're designed to detect things like airplanes. But parachutes tend to have a very large return, meaning that as soon as it opens, boom, you are about the size of an airplane, and you can be detected. So to get into places where you don't want to have it known that you're there, they will do this kind. When I asked them, how high do you jump, they just said classified, which told me that it was over 30,000 feet. Okay. And then they open depending on kind of where it's safe. Parachuting in the military has the highest casualty rate. Casualty is defined as an injury, not necessarily death. That's a fatality, okay? But a casualty, so the biggest problem is broken ankles, broken shins, broken knees, ACL tears, that kind of thing. So they try to train really hard for this, but sometimes you just can't avoid the trees or the rocks or anything else that you might be landing on. But yeah. Hats off to the men, women, and dogs of the United States military. Allowing it so that we can be here and argue about politics and other things. All right. Let's do a quiz. Not about the military or halo jumping. About work and energy. For the record, halo jumping is something I do not want to do. Going kind of light here. 2-point quiz. Quiz 8.1, 8.2. Even though it's a 2-point quiz, only one of these answers is correct. You here to fix our door?
They're coming either today or tomorrow.
Fantastic. My students have been asking, so
Yeah.
thank you.
Yeah. So it's just, it'll hold open and just stay open?
No, it just the switch doesn't work at all.
I think they turned the breaker off because that's what it was doing.
Oh, it's just staying
It
open.
was just staying
Okay,
open.
all right. But yeah.
That was a sub of ours, so they're coming.
Okay,
Take a look at it.
perfect.
I'm here to look for a leak.
All right, thank you. Think you've got it? 15 seconds left? Or do you need more time? More time. Okay. I went out to talk to the technician fixing the door.
Is there like air resistance or anything?
No. This may or may not be based on a true story. Because I was on the dive team. All right. Turn to your neighbors and give them that scared, haunted look in your eyes that he says, I don't know what I'm doing, and tell them what you got and why. Go.
Cancels out the formula of C. A. No, because you said we caught it. I think something about air resistance.
I just remember the bullet that he showed us with the
Free fall is the only thing that affects. And then I was also thinking like it's not by diving power is probably not high enough for even that factor or something.
So they're massive different natural synergies machines, so they should have similar air resistance.
All right, are we ready? See if we got this. How many of you say A is the correct answer? Okay, A is incorrect. Why is A incorrect? Gravity will accelerate all objects at the same rate regardless of their mass, right? If I drop a mouse or I drop an elephant, they're going to hit the ground. Now, that doesn't have anything to do with energy or work, does it? That's just the way gravity works. It's free fall acceleration, 9.8 meters per second squared. So we know A can't be the correct answer. For what it's worth, I had the better form and I reached first. Anyway, do both of the students have the same potential energy? What's potential energy? mgh. What's the same there? G and H, right? Same planet, same height of diving tower, but are the m's different? Yes. So do they have the same potential energy? No. Potential energies are different. All right. Do they have the same kinetic energy when they hit the water? No. Why not? There's two different ways to think about this. If they have different potential energy, they will have different kinetic energy because energy must be conserved, right? Whatever energy you start with has to be the energy you end with. So if one of them starts with, in this case, twice as much energy as the first one, it's going to have twice as much kinetic energy at the end. The other way to think about it is kinetic energy is 1/2 mv squared, isn't it? We know that the v is the same. We know that the half is the same, but again, the m is different, right? So we've got that. So that leaves D. Is this a true statement? Work is force times distance, isn't it? The distance to the top of the tower was the same, but which one does more work? The more massive one, working against their own weight. And believe me, I held that over the head of my friend all the time. I'm really surprised I didn't get beat up. But John was a good friend. If you stood Randall and I next to each other, that's basically the comparison here, right? So I was tiny, he was huge. He was like, I was like 110 and thin and scrawny and glasses, and he was like 200, 220, all muscle, 6'5", on the football team, had a girlfriend, like he was everything. All right. I don't think I stopped recording there. Congratulations, YouTube. We'll chalk that one up to my neck tattoos. All right. Another one that may or may not be based on a true story. It is based on a true story. Another one of my friends was in a wheelchair in high school. So this one, again, these are like just examples, variations on a theme, application of all of this conservation of energy stuff. And so where do you want to start? Like, you tell me what to write down. Are we going to do a picture first? We're going to do equation first? What do you want? Equation? Picture. Picture first. Okay. So there is a slope or a hill. So what does that automatically look like? A triangle. Okay. Something like that. Okay. So we got... Now, what is this story about? The wheelchair rider or the skateboarder? What's like all the information? It says the boy. It's awkward English here. The boy, a boy in a wheelchair. So this is about the wheelchair rider, isn't it? All of these numbers about the slope and the speeds and stuff, they're all about the wheelchair rider. So wheelchair rider starts up here, ends down here, right? And we need to know initial, final, and zero, don't we? So you tell me where they go. Initial at the top, okay. Final at the bottom, all right. Zero also at the bottom? I like it. Okay. So we got initial, final, zero. We could do you guys want numbers attached to the diagram? Do you want them somewhere else? Diagram? Keep hearing this side of the room, so we're just going to keep going their way. So let's see. So what's the initial speed of the skateboarder? It's not 0, right? So the V initial is 1.4 meters per second. The V final, they did give me a V final, didn't they? 6.2. Okay, 2.6 meters high and 12.4 meters long. This can be a little bit hard in words to convey, and so it can get lost in translation a little bit. And by that, I mean the translation between physics and English. So what does 2.60 meters high imply? Like, yeah, the vertical height of the slope, right? 2.60 meters high. And then 12.4 meters long. I think this is the one that gets mixed up. It's the length of the slope. It's not the horizontal leg of the triangle. The 12.4 meters long goes along this slope, this hill, this hypotenuse here. Okay, so you're sitting there on the exam. You're reading it and your mind goes blank or you can't decide what it's meant. What do? Drop the class. No.
Come back to it later.
You're on the exam. You don't have time. You ask me, right? This is one of the kinds of things that I'm not testing you about, right? Okay? If you can't understand the question or where a number applies, come up to me. More than likely, I will just draw right on your paper. It's this thing right here, right? So sometimes I might say no because maybe it's like critical to your conceptual application of the problem. But most of the time, if you're given a number and you're not sure what that number gets attached to or means or where it's applied, ask me, right? Just ask me during the exam. You don't have time to waste, right, on things like that. You've got to spend time on applying physics and doing some math, right? So please, I'm inviting you to ask me. I know other teachers have told you you're not allowed to ask any questions during the exam. Ask a question. The worst thing I will say is what? I won't help you. Sometimes I say I can't help you, but what I mean is I won't help you because I probably could help you. All right, so now that we got all that sort of worked out, there's one more, there's more numbers here, right? The mass is the mass. The 41 newtons, the heck is that? It's a constant frictional force. It's like they've lumped the friction in the wheel axles and the air friction. They kind of put it all together so that the math is easier, right, to deal with. That's 41 newtons, right? And it acts during the entire slope, doesn't it? The entire time that the boy in the wheelchair is moving. All right. I think we've kind of got all the numbers we could on that diagram. Kind of makes it a little bit sloppy, but that's all right. Work other plus energy initial equals energy final. By the way, if I ever write work NC, I'm sorry. Trying really hard not to do that. Work other is a grab bag for non-conservative forces. For you, non-conservative just means it's not gravity or a spring. Okay? Basically every other force. But sometimes I will, like, if you ask me on email, if you're asking me in GRASP or something, that'll slip out. Work other. All right. And a lot of websites and stuff will talk about, well, if the force is non-conservative, make sure you do the work. What they're trying to say is it's work other. It's not gravity. It's not springs. All right. All right. Is there any work other? You bet. There's that frictional force, right? So work done by friction 1. Okay. Initial energy. Is there any initial kinetic energy? Yeah, the boy's moving, isn't he? So there's definitely can't zero that one out. And potential energy initial, is the boy at 0? No, so there's going to be that. Okay. Energy final, is the boy moving? Yeah. And is the boy at 0? Yeah. All right. So now I've got to kind of look into the toolbox a little bit for the definitions of these different things, right? And figure it out. So work done by force 1. Well, I know work is force times distance, but this is a frictional force. So it's going to be negative, right? The frictional force points up the hill, but which way is the boy going? Down the hill. All right, and then this is 1/2 mv initial squared plus mgh equals 1/2 mv final squared. What am I looking for? Find the work he did in pushing forward on his wheels during the, oh. I should read my questions more often. What am I finding? Find the work. This is the work, isn't it? F1 and D together are the work. So it turns out that I don't need to write that down. I can just write work F1. So I'm going to go ahead and just kind of erase all this out. And just write work due to F1. This is something I've seen happen a lot. You'll email me, Mr. Bill, A plus hates me, and I did it all right, and I compared it there with people, and it's not giving me it. And I'll be like, is it asking for the work or the force? Right? And a lot of times students will have solved for the force or the distance or something, right? If it's just asking for work, leave the work term alone. That's your unknown, right? Your F times D together is unknown, but that's work, right? The work will be the difference in all of these things. If there were no friction, what would happen to all the kinetic and potential energy at the top? It would be exactly the same at the bottom, but it's not. This speed is different than it should be if there was no friction. So where's the work that friction did? It's the difference in energy that the boy had at the beginning versus the end. If you want to go and break it down, since we know the force, 41, you could find the distance, but then at the end, what would you have to do to find the work? If you have a known distance and a known force, how do you find the work? You multiply, right? I'm just saying you don't have to do all, well, I think part B we have to, right? But like, or, yeah, no, we're just finding the work. There is no part B. We're good. Just find the work.
We're finding the work that he did pushing down the slope, and we have the work.
Oh, geez. Thank you. I just didn't even read the problem, did I? I'm glad you're here. Because there's really two works here, aren't there? Yeah. So work force 2 times, oops, no, not times D. All right. Thank you. Work force 2. So we better write down work force 1. You know, it'd help if I actually turned my pages to the correct page. Is that the one? Maybe. Yeah, this is work force 1. So we can write this as negative F1D, which I was doing originally. So just ignore everything I said for like the last 2 minutes. And we'll blame that one on reading comprehension and steroids. Is it hot in here? Like really hot, like sauna hot? My wife and I have 2 things in common now. We both get hot flashes. She didn't think that that was sweet or empathetic at all. All right, so I'm now solving for this work done by force 2, right? What I said about don't break up a work if you're just trying to find work, that still applies, right? I don't need to break this up into force 2D, D. I can just find that work. All right, so rearranging, work done by force 2 is going to be equal to 1/2 mv final square. I'm moving anything that's not work force 2 over the other side. And this force, this work right here is negative. Why is that one negative? Friction. So that becomes positive F1D. And then I get a minus 1/2 mv initial squared minus mgh, right? So what I did is I chucked that one over, I chucked that one over, and I chucked that one over. Because it was negative, it became plus. Because that was plus, it became negative. And the same thing with the MGH. All right. Do I know everything there is to know on the right-hand side? It looks like I've got known everything's over there, right? I can make this a little bit shorter in my calculator. 1/2 m, and then I can do a v final squared minus a v initial squared. That's just bringing those and factoring out the like terms. It's not necessary. Plus f1d minus mgh. Okay, so I can put in numbers. 1/2, 47, 6.2 squared minus 1.4 squared, plus 41 times 12.4 minus 47 times Earth times 2.6. And assuming I wrote down all the right numbers, and assuming I can actually get them into my calculator correctly, which, by the way, is a lot of assumptions. And you know this now, right? Sometimes I wonder if this is the hard part of this class. When it looks so easy, but it's like by the time you get here, your brain's gone. It's a puddle of mush. An order of operations can be a really hard thing. What I got here was 168 joules. Scott could always beat me down a hill. Scott was my friend in high school who was in a wheelchair. And he had 2 wheelchairs. He had the one that he kind of used everywhere, but then he also had a racing wheelchair, which is the one that he did whenever we go out skateboarding with him. And it was one of those, so this is back in like the early 90s, right? And so it was like one of the very first like lightweight carbon fiber type wheelchairs. And we got really used to like disassembling and reassembling his wheelchairs, right? Getting him in and out of the car and stuff. And we always liked using the sporty one, his racing chair, because it was so easy, right? Like punk, and it just was, you pick up the whole thing with one hand and all that kind of stuff. So we would go out to run and track, right, for PE class, and we'd have to go run the mile. He did like 3 or 4 miles on his wheelchair in the time it took us to do 1 mile, running around. And he was paralyzed from the waist down, so he was like on top, nothing on the bottom, but up here. And he just head down and put his gloves on, and oh my gosh, made us all look like wusses. Anyway, Scott was a cool guy. What are we doing now? What time is it? Oh yeah, we got time. Let's watch people who are not enjoying doing physics do some physics. Okay, so we've been having trouble with the audio in this room. So I'm going to turn the audio down. It's going to be narrated by me. You'll have to listen to my melodious tones. Okay,
Raising
so
a mat
we have a track here, and you can see how the
increases its
track is divided into 3
gravitational
different
energy.
sections, and each of those
We'll
sections
use
has
this
a different
triple track
slope
to show that
on
this
it,
energy
okay?
is conserved as it
And what
changes
this
from
guy is
one
going to do
form
that
to
looks
another.
like he is thoroughly enjoying
We'll
life
release a rubber
is he is
ball
going
down
to take
each
that
of
ball
these 3
and he's
tracks.
going to put it at the top.
Each track
of
has
the
a similar
track,
downhill
okay?
section,
And he's going
but
to,
the uphill
and you
sides have
better
different
be
slopes.
very careful.
If a ball is released from the top
number
of
one,
each track, how
is
high
science.
will it rise
No
on the
smiling.
other side
Number
in
2.
each case?
Do not let that ball have any kind of initial kinetic energy, right? Your job's on the line. All right. So he's going to be very careful letting go of this ball, right? And he's going to roll it down. It's a little bit hard to see in the video, but there's actually 3 tracks here, right? There's 3 starting points, and each track goes up a different slope, right? And so he's going to roll it down, and the video editors are very kindly going to put a dot for the highest height, right, that the ball achieves. So the question for you is, this is not a quiz, just a what if, right? But to what height does the ball go on each of those sections of different slope? What do you think? Different heights or the same heights? Same heights? Why same heights? How much energy does the ball start with in all 3 cases? the same, whatever it is, it's the same as it has to have at the end, right? A little bit of friction in this problem, right? But we'll try to ignore that. Let's see what happens.
Here's the ball rolling
So there's
down the first
one.
track.
Thank you, editors. That is CGI, that red dot. Yeah, okay, be careful. Oh, good, okay.
Track.
Oh, looking kind of samey, isn't it? Right. We'll blame any discrepancies on the editors. Yeah. Oh, that one looked like it had a
The
little
third
initial to
track.
me, but we'll let it slide. You're okay. No smiling.
The ball rises to the
Good.
same height
Good job.
from which it was released.
You
in
can see
each
that
case.
one's a little bit low. Just a tad bit low, right? Why was it a tad bit low? Like more friction, like it had a further distance to go along the track, didn't it? Just a little bit more friction. And I know we haven't talked about rolling stuff yet. So. All right, so I just wanted to show you that. Energy is conserved. I think I can't do it in this room. They were supposed to put a metal bar up here to support like 1,000 pounds, and they never did. So I've got one of those bars in the lab room. So I think on Wednesday we'll do the pendulum conservation of energy demonstration. Okay, so save that one. For a room where it can be supported. We got no sink in here. We don't have any lab gas or lab air. This isn't the greatest room for lecturing on physics or biology or chemistry. Why would we want to do any of that in this building? Let's see here. What homework is due Saturday? Is that chapter 7? Okay. And you know chapter 8 to do on Wednesday because of the exam. So you really want to be done with chapter 7 and on to chapter 8. I wonder if I should call an audible here. You know what? I'll do this example because it does show what to do about springs. This is another one of those annoying problems that doesn't have any numbers in it, but I tried to indicate that the things you are given are in quotes, right? So we'll do it all symbolically, and if we had numbers, we could then put the numbers in to actually get the answer. But the more important thing here is the setup, right? So my gosh, what is going on? We've got a horizontal frictionless surface. Horizontal frictionless surface. Horizontal means it's perfectly flat, doesn't it? Okay. And it's moving along at some speed v naught. That's supposed to be a 0. Then it encounters a rough patch. And that rough patch has a length d and a coefficient of mu, which means that what is definitely involved? Friction. After the patch, the object hits a spring, I'm assuming compressing it, some distance, x, before the object comes to a complete stop. So what's its final speed?
0.
Comes to a stop. Find the distance it compresses. We're looking for x there, right? So let's see where we can get. That's our visualization. We need an initial. We need a final. We need a 0. Okay, so initial. Is this becoming a slightly stupid question? Hopefully it becomes fairly obvious after practicing this enough where you go like, oh yeah, it started here. Excuse me, so that's where I'm going to put my initial. Final, trust the whole, okay. When it first touches the spring or when it compresses the spring?
Compresses.
Let's go all the way for the compression. Let's trust it, right? It can do the whole thing. So this will be our final. Our 0 for gravitational potential energy. Is there any gravitational potential energy change in this problem? No, it's not going up or down. And so it doesn't really matter where we put 0, but if I put 0 right there, it means that the gravitational potential energy is going to be 0 no matter what, right? I don't have to worry about any numbers or anything. But there is another 0 we have to worry about because there's another kind of potential energy in the problem. Spring. You and I and nobody that does physics for the human race is allowed to put 0 for a spring anywhere other than its equilibrium position. That is fused into the potential energy equation and Hooke's law. So 0 for springs is always where the spring is like rest, where it's not stretched, it's not compressed. It's where the spring is applying no force at all, right? And then x represents the distance the spring is either stretched or compressed. But we're not allowed to pick 0 anywhere else. Your 0 for gravity can be different than the 0 for the springs. They do not have to be at the same place. It's just that you are not allowed to choose 0 for springs. You can only choose 0 for gravity. All right, and then we've got work other plus energy initial equals energy final. I always try to spell out the word other because if I do work sub O, it looks like initial work and then I get lost. Is there any work other in this problem? Friction, right? That's definitely something that's not gravity or spring, so yeah, work done by friction. Okay, does it have initial energy? Is it moving? Yes. Is it at 0? Yes. Is there a spring at the initial point? No. So this must be just kinetic energy initial. And do plus 0 if you want to remind yourself that you checked the other two. All right, at the final position, what's the kinetic energy? 0. It came to a stop. What's the gravitational potential energy? 0. What's the spring potential energy? Not 0, right? Why is the spring not 0 at the final point?
Because it's compressed.
It's compressed, right? We've squished on it. So we're going to do potential energy spring final. Okay, now I got to go through and figure out what all these things are. The work done by friction will be the force of friction times the distance it traveled, and because it was sliding, negative work, plus the kinetic energy initial, 1/2 mv initial squared, equals, and then what's the potential energy for a spring? 1/2 kx squared. Okay, so that's what I've got. Is there anything I don't know in this problem? So I don't know x, but that's okay. I'm solving for that, right? I have k, that was given. 1/2 was given. V initial was given. Mass was given. I know a half. I know how far it was. Oh, I wasn't given the friction. We were given the coefficient and its friction, so therefore it's thank you. Right? If a force and a coefficient are mentioned, there's probably a normal force hiding somewhere. So minus mu times n times d. But what's the normal force? If we're just on a flat surface, it's just going to be mg, right? Unless there's another force pushing down or pulling up on it or something, right? But if it's just all by itself, it's going to be mg. So this is mu mgd plus 1/2 mv initial squared equals 1/2 kx squared. All right. Just a side note on that, because in your homework, I think you have problems where you will have things on slopes that have friction. So you have the normal force, you've got the weight, you've got the friction acting backwards here, right? If you're on a slope, is the normal force mg? What is it? It's mg cosine theta, because you'd have to break up the gravity. This one becomes mg cosine theta, And so a normal force is mg cosine theta in general for energy problems. You can, if you want to, continue to use this for every normal force you run into. In the case of this problem, what's the angle of the surface? It's 0. What's the cosine of 0? 1, right? So that's why it's just mg. Personally, half the time I can't remember that the cosine of 0 is 1. I sometimes think it's 0, and then I get bad answers. So I tend to compartmentalize by saying, okay, if it's flat, it's mg. If it's anything else, it's mg cosine theta. Just because I know myself and I'm going to mess up. All right, so now I think I've got everything in there that is known, right? I just need to solve for x. Well, x squared's got a half and a k on it, right? So I've got to get rid of those. How do I get rid of a half? Multiply everything by 2, right? How do I get rid of a k?
Divide by 2.
Divide everything by a k, right? Okay, so let's go in here, multiply everything by 2. And then divide by k. So what does that leave me with? I'm going to flip my equation around again because my teachers always yelled at me if my thing I was solving for wasn't on the left. Turns out it was a lie, but it's habit now. mv initial squared minus 2 mu. They also taught me that I had to write the negative things second, but that was also a lie. All over k. All right, so now how do I get the squared? Square both sides. Or not square both sides, but take the square root of both sides, right? So there we go. That should be my answer. If I had numbers, I'd stick it in, but I don't care about numbers. Numbers are dumb. Let's just check a couple things. K is this spring constant. It's the thing that tells you how strong your spring is. So if K is bigger, like it's a really stiff spring, what will happen to X? It'll be smaller. And we know a big number denominator means small number answer, right? Does that make sense if a spring is really, really pushy, that it would stop it really fast? But if it was more like Jell-O or a Slinky or something, right, it would take, right? Okay. So that follows. This work done by friction part, right? Because that's where this friction is sitting. Notice how it's a negative. So what is that telling you? The more friction we have, the less the compression will be. Does that also go with intuition? The more friction there is, the less energy there would be to compress this. Like it would slow down more in the friction section, and so therefore it wouldn't compress the spring. I like that. And then if we start with more velocity, it's going to be bigger, right? So a lot of these things, the form of that is something that makes sense to me and flows from what I understand about energy and work and things like that. So feeling pretty confident about that. And I've had these notes now for 5 years, and nobody's corrected me. So what?
This might just be a notation thing, but couldn't the x just be delta x?
Sure. Yeah. I mean, it's a change in position, but the first x is 0 by definition, because springs always start with an initial compression of 0. Kind of like time always starts at 0 time. In the case of springs here, the 0 point is set for us. Yeah, we can't choose that 0, so the initial is 0. I mean, the final could be 0, I suppose. The clown problem that I did the clown problem, right, where we launched them out of the cannon. There we had compressed the spring initially, but the final was 0. It's always referencing the center of the spring. So. All right. I hope to see you in GRASP tomorrow, but if not, I do hope you have a good weekend. Get your Chapter 7 homework definitely done so you can be working on Chapter 8. That would be ideal.